So tonight we are looking at how we are going to metabolize food. So we actually kind of talked about this in our exercise physiology class. You remember we went through the entire GI tract. So we're going to go through that again. We're talking about this idea of catabolism, right? Breaking stuff down. And hopefully by revisiting this will kind of give us a little bit more insight into how we build stuff up anabolically when it comes to, like, making materials, right? So we are looking at nutrients and their journey from ingestion to becoming part of our metabolism, right? How do we take food in, break it apart to where it's not really food anymore, it's just base components, and then we take those base components and build them back up into a different shape in our version of, like, energy, right? So that's kind of what we're looking at today. So our objectives, we want to understand what happens to nutrients after they are ingested and how they're broken down, how carbohydrates are absorbed, how fats are absorbed, how proteins are absorbed by our body, how minerals, vitamins, and waters is also absorbed and then transported. And then we will look at, like, energy metabolism, why it's so important, how we generate it, looking at how our cells make ATP. So we will review our energy systems for the last time for quite a while, which is, I'm sure everybody's excited about that. We'll leave it alone after this. And then we'll talk about, like, which metabolic pathways are used with, like, specific nutrients, right? So I got a fun video to show you guys today. It is, we're going to watch actually we're going to do a double crash course video here. Digestive system. So this is going to take you through the digestive system, start to finish. We watched this video already, but this is actually going to be kind of a two-parter. This is a pretty fascinating one that is from their other course. So let's see here. We need that, and then here we go.
Healthcare is backwards. Everyone knows it.
I swear to God.
But it's not for the reasons you think.
Forward, get out.
It's not. We all have our.
Never going to go to a forward place ever. God, they send me ads every day. All right, so here we go.
We all have our reasons for eating nachos at 3 in the afternoon. I happen to have my own. And don't ask, it's personal. But more generally, we all eat any kind of food to accomplish two simple things: to obtain the energy we need to stay alive, and to get the raw materials required for building all of our tissues and stuff. That's because when it comes down to it, both you and the food you eat contain those two same things. Both you and food are made of stuff, by which I mean matter, made of certain kinds of atoms, and both you and food have energy stored in the bonds between those atoms. So all living things need to take in stuff and energy and convert it into slightly different stuff and energy. And you can get some of the things you need pretty easily, like in order to get oxygen for respiration, to unleash the chemical energy in your food, you just have to inhale. But you can't just breathe in the stuff you need to build DNA or actin or a phospholipid bilayer. So, how does your body really acquire stuff? That's where the nachos come in. This cheesy, crunchy dish is made of all different kinds of biological matter, like carbohydrates and fat and protein, and it contains a certain, probably shocking amount of calories, which is how we measure energy stored in the chemical bonds in food. So if I take like a 100-calorie bite of nachos, which probably with this much cheese wouldn't even be a very big bite, I can convert the chemical energy stored in those carbohydrates and proteins and fats to feed my muscle and heart cells and maybe like walk a mile, an activity that happens to use about 100 calories. But I can't just swallow the nachos and watch the lump of them travel straight to my heart or leg muscles. In order to actually use this food, I have to convert the biological matter into something my body can work with on the cellular level, which, as you know, is pretty darn tiny. And the work of converting the stuff in food into the stuff that's in my body is done by my digestive system. Human digestion occurs in 6 main steps, some of which you are intimately familiar with, others less so. But every step of the way, your body is working to reduce all the different kinds of molecules in food into their tiniest and most basic forms. The first step is probably everybody's favorite. When When it comes to what your digestive system ultimately does, just think of it as a sort of disassembly line. You could have an order of nachos with the works. I'm talking beef and onions and sour cream and slices of jalapeno, and your digestive system will deconstruct it, both mechanically and chemically, one step at a time. It's gotta do this because your cells work best with materials that are in their most basic form. Your digestive system reduces food to that level in two main ways: by physically smashing it to smithereens and by bathing them, as much as it can, in enzymes. Enzymes are proteins that living things use as catalysts to speed up chemical reactions. When used in digestion, enzymes break down the large molecules in your food into the building blocks that your cells can actually absorb. Those large molecules are called biological molecules, also known as macromolecules, and everything that you eat, I hope, is at least partially made of them. And there are four main kinds. You got the lipids, the carbohydrates, the proteins, and the nucleic acids. Each possesses its own density of chemical potential energy, or caloric value. Like, for example, 1 gram of carbohydrate contains about 4 calories, while a gram of fat contains about 9 calories. But many of these biological molecules are polymers, or sequences of smaller molecules, and your cells aren't really equipped to take them up whole. What your body traffics in are those polymers' individual components, called monomers, and there are four main kinds of those too: fatty acids, sugars, amino acids, and nucleotides. The simple idea behind the whole digestive system is to break down the polymers of macromolecules in your food into the smaller monomers that your cells can use to build their own polymers, while also getting the energy they need. And what your body needs to build at any given moment is always changing. Maybe you need new fat stores so you can have energy to run a marathon, or new actin and myosin to build bigger muscles, or more DNA so you can replace the skin cells you scraped off your knee when you fell, or more enzymes so you can digest more food to get more building materials. To meet your body's constant and constantly shifting demands, your digestive system requires a lot of organs that perform a lot of specific tasks to break down and absorb the right nutrient at the right time. Now, I'm quite sure that you're familiar with the key players here. They're the hollow organs that form the continuous tube that is your alimentary canal, aka the gastrointestinal tract, which runs from your mouth to your anus. It's worth pointing out that these organs are hollow because you are basically hollow too. Your digestive tract is really just one unbroken, insulated tunnel of outside that just happens to run through your body, and it's open at both ends. You're a donut. So the layer of stratified squamous and columnar epithelial cells that line your tract is actually a barrier between the outside world and your inside world, but it's a barrier that allows for the selective movement of materials between them. It's these hollow organs that do the actual moving, digesting, and absorbing of food, and they include your mouth, pharynx, esophagus, stomach, and small and large intestines. In your mouth, in your esophagus, and at the other end of things at your anus, you have stratified squamous epithelial tissue, just like your epidermis, to help resist the abrasive action of, like, chewing like corn chips, maybe. From your stomach on down, though, the inner GI tract is lined with simple columnar epithelial cells, which secrete all sorts of stuff and which absorb and process various nutrients. Most of these columnar cells secrete mucus, which lubricates everything and protects your cells from being digested by your own digestive enzymes. So the innermost epithelial layer of the tube is known as the mucosal layer, and it contains some connective tissue as well, which supplies it with blood. Surrounding the mucosal layer is the submucosal layer, made of loose areolar connective tissue, which helps provide the elasticity that the tube needs when you eat a whole pizza in one sitting, and it contains more blood vessels. And outside that, you have the muscularis external layer, which, as you might guess, is where you find the muscles responsible for moving food through your tube. Beyond these layers, the GI tract gets tons of support from the accessory digestive organs like your teeth and your tongue, your gallbladder, salivary glands, liver, and pancreas. They're kind of like a pit crew, and they mostly help by secreting various enzymes that help take apart food as it comes down the tube. Together, these two groups on the digestive disassembly line work in 6 steps to destroy your food and release and recycle its nutrients. First, of course, you gotta introduce the food to your digestive system. What you know as eating or ingestion is basically just creating a bulk flow of nutrients from the outside world into your tissues. This is where the work of disassembly begins, in your face hole, which scientists call your mouth. Now, we're gonna get into the details of what happens here another time, but remember that food disassembly is both mechanical and chemical, so your teeth pulverize the bite of nacho or whatever, while your salivary glands begin that food's hours-long enzyme bath. But the food at this point is not nearly micro enough to be of any use to your cells, so you have to move that mush further down your tube. This stage is called propulsion, and its initial mechanism is swallowing, which, as you know, is a voluntary action, but then it's quickly turned over to the involuntary process of peristalsis. In peristalsis, the smooth muscles of the walls of your digestive organs take turns contracting and relaxing to squeeze food through the lumen, or cavity, cavity of your alimentary tract. Waves of peristalsis continue through the esophagus, stomach, and intestines, and they're so strong that even if you were hanging upside down while eating your lunch and drinking your tea, the food would still soldier on, fighting gravity, and eventually make it to its final destination. Don't do that, though. There's other reasons why you shouldn't be upside down. Anyway, all of this shipping and handling mechanically breaks down the food even more, and even after it goes through the stomach and its gastric acid, the mechanical work still continues once it reaches your small intestine, as more smooth muscle segments push the food back and forth to keep it crumbling up. The goal of all this pulverization is to increase the surface area of that bite of food by breaking it down into increasingly tiny pieces to prepare it to encounter more enzymes in step 4, chemical digestion. Really, the actual process of digestion only occurs when the main action becomes more chemical than mechanical. And here, the accessory digestive organs, namely the liver, pancreas, and gallbladder, secrete enzymes into the alimentary canal where they ambush the mush and break it down into its most basic chemical building blocks. Like I said before, our cells prefer to do business in the basic currency of monomers, like amino acids, fatty acids, and simple sugars, and digestion allows for the absorption of those nutrients as they pass from the small intestine into the blood by both active and passive transport. Once those nutrients are absorbed by your cells, you can finally use the energy inside of them or use them to build new tissues. The absorption of the nutrients is the goal of the entire process. But of course, it is not the end of it. Once your body has sucked out all the nutrients at once, indigestible substances like fiber are escorted out of your body. Yeah, I'm talking about pooping, or defecation. And that is the end of the digestive line, unless you are a capybara or one of the other animals who make sure that they get the most out of their lunch by giving the whole process another round and practicing coprophagia, aka eating their own poop. Now, you should notice here that some of the processes of digestion occur in just one place and are the job of a single organ, like hopefully you're only ingesting through your mouth and eliminating from the large intestine. But most of these 6 steps require cooperation among multiple organs. For example, both mechanical and chemical digestion start in the mouth and continue through the stomach and small intestines, and some chemical breakdown continues in the large intestine thanks to our little bacterial farm there. Over the next couple of weeks, we're going to take you and your nachos on a stroll through your digestive system and see who's doing what, where, how, and why. But for now, I got some nachos to finish, so I gotta go. And eating those nachos, as you learned today, will provide me with energy and raw materials by first ingesting something nutritious,
All right, so that's a good chunk of the digestive tract. Now we got to kind of look at the second half of it, which is all the, that's kind of the physical, mechanical part of it. Let's look at the more chemical side of it.
Introducing Rascal.
I always find
Rascal
like
makes unique gym
the
wear
best
for
part of these
lifters.
videos.
You know,
team.
in the summer of
How much fun animations you're gonna get. But this right here, the story that this one opens up with is a really cool story. So talking about chemical breakdown, listen to this nonsense. I actually remember learning about this in 5th grade. Our teacher told us this story when we were learning about health for the first time. But here we go.
In the summer of 1822, a French-Canadian fur trapper named Alexis St. Martin was going about his business near Lake Michigan when he was shot by a hunter. Right in the stomach. The wound was severe, and everyone expected St. Martin to die that night, but he didn't. A local army doctor named William Beaumont kept him alive. In fact, Beaumont performed so many surgeries on the injury over the next several months that he decided, somewhat questionably, to just keep St. Martin's stomach wound open. St. Martin was left with a hole, or fistula, in his abdominal wall, which allowed anyone to see right into his stomach. Now, it's probably hard to work as a fur trapper with a hole in your guts, but Beaumont saw, or possibly created, an opportunity. He hired St. Martin, technically as a handyman, but really as a guinea pig. Over the next several years, and some 238 experiments, Beaumont recorded what St. Martin ate and what his stomach did to his meals. Sometimes they just skipped the eating part altogether and just shoved some food tied to a string right into the guy's gut hole. Beaumont took samples of gastric juices and had them analyzed by chemists, something no one had ever done before, and he also noticed that St. Martin's digestion slowed at certain times, like when he was sick or stressed. I mean, like beyond the stress of having a gaping hole in your abdomen. Through his somewhat questionable research, Beaumont discovered some major secrets of the digestive system, like that the stomach's extremely strong acids and muscular contractions break down food, and that some foods are more digestible or less digestible than others, changes, and that the brain can affect the stomach. Beaumont's findings, as well as his methods of clinical observation, revolutionized the field of physiology. And St. Martin? Don't worry about him. He lived to be 83 years old, had great health.
Somehow.
And a hole in his guts. Now, I sincerely hope that you can't actually see what's going on in your stomach, but let me tell you, the story there is epic. In your digestive system's mission to disassemble food into its tiniest, most basic molecular forms, the stretch that runs from your mouth to your stomach unleashes all of the mechanical and chemical powers at its disposal. It physically roughs up food, douses it in protein-loving, acid-triggered enzymes, reduces it all into a creamy paste, and as a bonus, because it likes you, it also kills a whole host of harmful invaders that, for whatever reason, found their way through your face and into your tube. But your stomach's not the end of the line for your food, unless it is. I mean, most of the time, everything from your mouth to your stomach prepares food to be absorbed by your tissues, but sometimes food finds its way back up. Yeah, in case the story of Alexis St. Martin didn't make you want to do this already, now I'm talking directly about vomiting. Let's begin with the beginning, with your mouth, aka your oral or buccal cavity. Now, we don't usually think of it this way, but that is where digestion starts, the mechanical and chemical breakdown of food through chewing and enzyme action. The inside of your mouth is lined with a tough, thick layer of stratified squamous epithelium that can stand up to lots of friction, like getting scraped by tortilla chips and like grilled cheese sandwiches that maybe were cooked a little too much on the top. Your anterior hard palate and the flexible posterior soft palate form the roof of your mouth. The hard palate provides like a hard surface for the tongue to mash food against, while the soft palate forms a movable fold of flesh that reflexively closes off the nasopharynx when you swallow, so food gets directed down your esophagus and not up into your nasal cavity. We all know what teeth are for, and you have roughly 32 of them in your basic types that help you masticate or chew your food. The tongue lives on the floor of your mouth and is basically just a big muscle that grips and constantly repositions your food as you chew. The resulting ball of mush actually has its own special name. It's a bolus, and the tongue rolls it back to the pharynx in preparation for swallowing. But that's just the physical action that goes on in your mouth. Just as much destruction is taking place through chemistry. The bolus is broken down with the help of 3 major pairs of salivary glands that churn out an average of 1.5 liters of slightly acidic saliva every day. More than 4 soda cans worth of spit per day. And all that saliva delivers enzymes like salivary amylase, a digestive enzyme that breaks down starches into glucose monomers. Now, once the food enters the pharynx, it's propelled by peristalsis into the esophagus, which, except for the little sphincter at the end that keeps food moving in the right direction, is really just a glorified laundry chute lined with smooth muscle. The only time you probably even remember that you have an esophagus is when something's stuck in there, or if you're feeling intense heartburn, or if you just puked. But moving on. Assuming you have not just puked, then the bolus moves on to Dr. Beaumont's ticket to fame, the stomach. The stomach is the stretchiest part of your digestive tube, capable of holding 2 to 4 liters of material at any given time. 2 to 4 liters. That is a lot of nachos mixed with spit. But of course, it's much more than just a storage tank. It's lined with the same 4 main layers found through most of the GI tract: the mucosa, submucosa, muscularis externa, and serosa, but it's got a few special modifications. For one thing, the muscularis includes an additional layer of smooth muscle that gives it extra strength, allowing the stomach not just to hold materials, but to actively smush them around. And the inner mucosa is made up almost entirely of mucus cells, which produce a protective coat that keeps the stomach tissues from getting digested along with your lunch. This inner lining is dotted with millions of tiny, deep gastric pits, which lead down to tubular gastric glands. These glands, in turn, contain various types of secretory cells that brew up some of the most potent chemicals in your body. For example, your stomach has parietal cells that release hydrochloric acid, a substance more acidic than battery acid, which lays waste to most of the bacteria, viruses, and other stuff that could make you sick. It also helps denature or change the shape of proteins to make it easier for enzymes to digest them. And maybe more importantly, when the hydrochloric acid is combined with pepsinogen, an inactive enzyme that's secreted by another kind of stomach cell called chief cells, the mixture creates the protein-digesting enzyme pepsin. Together, this superpowered acid and protein-hungry enzyme can annihilate nearly anything they encounter. This was apparently something that Beaumont observed firsthand by dropping hunks of meat into a cup filled with St. Martin's personal gastric fluids. He watched the gobbets of food dissolve over time, which is partly how he discovered the stomach's role in digestion was as much chemical as mechanical. But with so much mind-blowingly powerful stuff at your stomach's disposal, somebody down there has to be in charge. So your gastric glands also contain enteroendocrine cells. These cells release regulatory hormones like serotonin and histamine, which act locally to trigger other cells to, say, release more acid or contract muscle tissue. And when the time comes to tamp the action down, they secrete other hormones like somatostatin to inhibit secretions. And then there are G cells, which produce the most important hormone for stimulating gastric activity, gastrin. Most signals that increase stomach activity get the job done by increasing the secretion of gastrin, which then stimulates the release of other gastric fluids as well as stomach muscle activity. Now, if the smell of baking cookies has ever made your mouth water and your belly grumble, then it might not surprise you to learn that these stomach secretions are ruled by neural mechanisms as well as hormonal ones. In fact, stomach secretion occurs in 3 phases based on where the food is sensed: the brain, the stomach, and the small intestine. The cephalic phase is the one ruled by your brain, and it kicks in when you first see, smell, taste, or even think about food. That sensory input gets relayed to the hypothalamus, which stimulates the medulla oblongata, which then taps the parasympathetic fibers in the vagus nerve. From there, the signals are sent to the stomach with the word that, hey, we think that maybe cookies are on the way, so you might want to prepare yourself. Now, this is a conditioned reflex, so it only works if you want to eat the food in question. If I happen to be super full or not feeling well, or somebody puts a pile of squid eyeballs in front of me, the cephalic phase isn't gonna happen. And no offense if squid eyeballs are totally your thing, they're just not my thing. But say I eat the plate of squid eyeballs anyway, because I'm trying to be polite. Well, even without the cephalic warm-up, when that food hits my stomach, local mechanisms, both neural and hormonal, jumpstart the gastric phase. For the next few hours, as my stomach grows distended from the food, it activates stretch receptors that again stimulate my medulla and get my vagus nerves to tell my stomach to turn up the juice. At the same time, the secretion of gastrin is activated by other signals like the rise in alkalinity caused by the stomach acid getting neutralized as it does its job. Conversely, as stomach acidity increases, it inhibits the release of gastrin. Now, the third phase of gastric regulation, the intestinal phase, speeds or slows the rate in which your stomach empties so that the small intestine doesn't get too overloaded with too much acid or with the creamy paste that your stomach turns your food into, also known as chyme. Now remember, not a lot of absorption actually occurs in the stomach. The stomach is more like a decontamination tank. Sure, it pummels your food down to a paste, but it's also where your body tries to obliterate any nasties that could make you sick. As long as food is still in there, your body has a chance to kind of size it up and feel it out, and it reserves the right to eject anything that it feels is potentially dangerous. Lots of factors can trigger the stomach's urge to purge or vomit, but the most common are simply ingesting too much food or eating some kind of irritant or toxin, like those produced by bad bacteria, too much alcohol, certain drugs, or unappealing foods. Of course, if you've ever puked in a moment of trauma or stress, you know how emotions and anxiety can also trigger your stomach to launch its lunch. That's the brain influencing the cephalic phase of gastric regulation again by sending extra fight or flight signals to the stomach. Beaumont noticed this mind-stomach connection whenever St. Martin's digestion was affected by illness or stress. Something you'd think he'd have felt every time that doctor came at him with some meat on a string. If you were able to keep down your lunch today, you learned how mechanical and chemical digestion start in the mouth and continue in the stomach, where food is pummeled by acids and enzymes and turned into chyme. We also looked at the stomach's cephalic, gastric, and intestinal phases of digestive regulation. Thank you to all of our Patreon patrons who help make Crash Course possible, not only for themselves, but for everyone through their monthly contributions. If you like Crash Course and want to help us keep making videos like this one, you can go to patreon.com/crashcourse. Also, a big thank you to Sigmund Lervogue, Alexis and Brian Carpenter, and Luke Peterson for co-sponsoring this episode of Crash Course Anatomy and Physiology. This episode was filmed in the Dr. Cheryl C. Kinney Crash Course studio. It was written by Kathleen Yell, edited by Blake DiPastino, and our consultant is Dr. Brandon Jackson. It was directed and edited by Nicole Sweeney. Our script supervisor was Valerie Barr. Michael Aranda is our sound designer, and the graphics team is Thought Cafe.
Okay. I was trying to make sure I show the credits and stuff for doing these videos. So, a lot of stuff to talk about there. How weird is, I remember learning about William Beaumont when I was in school. I just remember hearing a story about a guy who had a hole in his stomach, and this doctor who would like put food on a string like into his stomach to digest. Um, let's go ahead and break everything down, right? So nutrients are, we say, like, we go back to that human donut analogy, right? They are outside the body until they are absorbed across the membrane into the actual blood stream. That's when they are sort of entering your actual body, right? Once they're absorbed, whether it's through lymph or through your blood or whatever, now it's like inside of you, and you can use all those materials to, produce metabolism. So digestion is the process of like segregating food into its little tiny itty bitty units, right? We take carbohydrates, we turn them into glucose, right? Into monosaccharides. We take proteins, we break them down into amino acids. We take fats and we break them into fatty acids. And once everything is, nice and small, now it can work its way into my bloodstream, right? So when we're looking at the digestive tract, it's going to start in the mouth. That is where the very first process of digestion is going to begin. Because remember, digestion is basically, it's a de-assembly line, right? So you're going to chew everything up and break it into pieces. Meanwhile, your spit, your saliva has a lot of enzymes in it. So there's a little bit of chemical breakdown that happens there as well. And then it will move into the rest of the GI tract, right? Or gastrointestinal tract, or, alimentary canal, if you want to call it that. So digestion is the segregation of food into its basic components. We're breaking them down so that, they are so small, they can literally pass through our cell walls into our actual bloodstream, right? And your blood cells are some of the smallest cells in your entire body. So, being able to transport that with this little tiny cell, these units need to be pretty freaking small. That's why we're breaking them down into, just chemicals rather than leaving them as like food. So then you're going to have your gastrointestinal tract, or your GI tract. It's going to consist of your stomach. Then it's going to move into your small intestine, and then it will move into your large intestine before it'll kind of exit out of the body, right? So your stomach is this kind of pouch that has all the, it's very good at creating these materials that break foods down. It creates hydrochloric acid, which is, so freaking acidic that, it literally just eats away at our foods. But then it also creates things like pepsin, which helps digest proteins, remember the slight difference between like carbohydrates and proteins. Proteins are held together with what's called a peptide bond, where it's just a little bit of a stronger version of a bond compared with your typical just like glucose bond that you're going to find. And so it's a little bit harder to break proteins down. That's why we need to have this extra enzyme there. So your stomach is filled with hydrochloric acid and other materials that break food down and chemically alter it until it eventually becomes this kind of wet, soupy mixture that we call chyme. And chyme is, if this is going to get gross, but if you've ever had food poisoning and it's come out the back end like soup, you're basically seeing chyme. It's food where, it's what used to be food that is now this just kind of liquid material. And that's normally like where our nutrients get extracted from, which dehydrates it and turns it into like an actual stool. But that's not the case if it's still chyme. So chyme is this kind of wet, soupy mixture. And then that chyme is going to move its way into your small intestine. This is the portion of your GI tract where really like digestion and absorption occurs. There's a little bit more digestion that occurs here, like for instance, fats are getting broken down in your small intestine. Your stomach acid doesn't do a great job on fats. Does a really good job on proteins. Carbohydrates got broken down a little bit by your saliva and then a little bit further in your stomach. But any of those carbohydrates that survived and didn't get fully broken down, or any of the fats that didn't get broken down, they're going to finally be, busted up into their individual components once they get to your small intestine. Because your pancreas is creating little enzymes that are helping break down any carbohydrates that survived, and your liver is creating bile, which is this material that emulsifies fat. So you're going to see some digestive enzymes in there. Those are coming from, like I said, your liver. Your liver is an accessory organ that creates bile. Bile's job is to emulsify fats, right? If we look at like emulsified you know, what that means is you had like a big fat molecule, you know, something kind of like this. Oops. You know, big fat globule, and then you have a little bit of biosalt, which is going to get in there and break that apart. And so now you've got, you know, much smaller, much more manageable, emulsified little fat droplets instead of like a big fat. So that's how emulsification works, and that's why, you know, when you dump like oil into water, it all kind of stays together. But if you mix that oil, oil, water, and dish soap, you can see, right, like these are all separated because there's the oil on top. But if you were to pour a little bit of dish soap in there, it would all start to mix together. And it's kind of a fun little science experiment that like kids will do every now and then. This is actually kind of cool. I've seen this before, where you make a you make kind of an interesting lamp here. These are all very different density things, you know. So milk is actually more dense than like a cherry tomato. Maple syrup is more dense than that. It's kind of fun. Like you can see all these different layers here, and then, you know, ping pong ball is not very dense because it's mostly empty air, you know, and then like a freaking, I guess, a bolt here. I don't know. But that's looking at like different densities. I don't know. That's a sidetrack, I guess. Liver's job is to emulsify stuff. If everything was broken down small enough, it would all mix together much more effectively. And so that's what we're seeing when we talk about like emulsifying. So when you have like a large fat that didn't get broken down by your stomach, that's okay because your liver creates that bile. Now, it can't necessarily hold on to bile. It doesn't store it very well. It just kind of produces it and passively puts it into your small intestine. So luckily, we have another accessory organ that is attached to your liver called your gallbladder. Your gallbladder is this little pear-shaped organ. Its job is to store up bile salts. And so when your liver creates bile, it puts it into the gallbladder instead, and then the gallbladder holds on to it, and then the gallbladder is what actually drops it off into your small intestine. So it doesn't make anything of its own, but it is a very important part of digestion. Let's say you have to have your gallbladder removed. Well, that's okay because it doesn't really produce anything by itself. But removing it means that we have to connect a duct straight from your liver straight into your small intestine, which means if you ever have like a really super fatty meal, you might have trouble digesting some of those fats because you just don't have any storage. You know, so you got to kind of get it at the right time. And then your pancreas shares a duct with that whole area as well. Your pancreas is nearby. Normally, we think of the pancreas, we think of the fact that it's creating things like insulin and glucagon that is helping us, like, you know, regulate our blood sugar levels. But in the process of digestion, your pancreas is releasing enzymes into your digestive tract, which is helping break down carbohydrates and proteins. So there is a little bit there. Now, on the inside of your small intestine is trying to absorb as many materials as possible, which means that it needs to have a massive amount of surface area. You know, if you look at like what your small intestine looks like, it's all of these little folds here, and each of those folds have these little tiny villi, these little projections from them. And then inside those villi, you can see there's capillaries where, you know, nutrients and blood flow exposure is happening. And then also lymphatic fluids to, you know, keep the whole area kind of moist. And so when you look at all those folds, that massively increases the surface area. You know, this would take a lot longer to paint if you're trying to get every little nook and cranny filled compared with something that, you know, might be smooth instead. So those little folds are called villi, right? And villi are these little rod-shaped projections that cover the walls of your small intestine. And this is the actual site of absorption. This is where chemicals are passing, you know, from one side of the wall. You can see here, right? Each of these individual little cells here, right? Materials are able to actually pass into those cells and then they are handed off into the bloodstream. And then all of a sudden, like once in the bloodstream, it's like, gets sucked in and, travels to wherever it happens to be going, let's get that glucose down to my legs because I'm doing some squats. You know what I mean? So that's what we're looking at in terms of increasing that surface area. And then eventually we will end in our, large intestine, right? And this is the last portion of your GI tract. This is taking any undigested or maybe like semi-digested foods. If anything didn't get absorbed by your small intestine, it's going to go into your large intestine, and your gut bacteria is going to help break that down until it is, fully broken down. Some of those materials will be absorbed as well. But for the most part, like maximum absorption really takes place in the small intestine. The one thing your large intestine does absorb a lot of are water and electrolytes. So this is where you drink a substantial portion of your water, and water is making it into your bloodstream. It is happening in the large intestine. We're also pulling all the water out of that chyme. Remember, chyme was this wet, soupy mixture, right? So as we pull water out of that, we are dehydrating it, right? And so dehydration synthesis, where molecules that don't have any water between them are attracted together. And so then they like slam together and become like a solid. And that is how we create our stool, right? We're pulling out all that fluid. And that's also where we absorb any remaining electrolytes, which are, sodium, potassium, magnesium, things like that. Certain minerals that are really like evenly distributed throughout like water and fluids. So, sometimes you'll hear people, who are dehydrated will have like gastrointestinal problems, and it could be, vice versa. So we're absorbing the final parts of our water into our bloodstream. We're getting any remaining electrolytes in there. For the record, there is an accessory organ that is attached to your large intestine called your appendix. We didn't really know what the appendix did for a really long time. Like I was taught in school that we don't know what it's for, which is why you can have your appendix removed pretty easily. But the new sort of prevailing theory is that your appendix houses your gut bacteria cultures. So if you ever get sick and you lose a lot of food out the back end, your body is not being choosy about how it gets it out of your body. It just wants it out. So what ends up happening is it, excretes all of it, and you lose a lot of your good gut bacteria that you actually need for the process of digestion. So the idea is that the appendix has some backup copies of that bacteria to get those cultures started again. So it's an accessory organ that we think is responsible for housing bacterial cultures that will aid in digestion.
Question. Okay, so what happens with the appendix that gives you so much pain that makes them want to take it out? I mean, what bacteria override?
It can basically get like infected. This is bacteria, right? That's so when you have to have like your appendix removed, it's where your bacteria has basically gone rogue. And it's starting to do what bacteria does, which is, take over tissues and, eat them. So when that happens, your appendix can burst. And then it basically puffs up because it's filling with like gases and stuff. Because that's the other thing bacteria do. This is why gases formed during sourdough bread. When you look at like making sourdough bread, you look at it in this jar here, right? There's all these little air pockets. Those air pockets are coming because like gases are basically expanding because of all the bacteria that's in this bread and yeast and stuff. So that, if that puffs up your appendix and your appendix bursts, right? All that bacteria is now suddenly like released and it's making you sick. It's very dangerous. Does that make sense?
Yep. Thank you so much.
No problem. That's my best understanding of it, at least. I will admit I'm definitely no expert on appendicitis. But I believe that's what's happening. All right, so now let's go ahead and look at our nutrients again, right? So carbohydrates, and by the way, we're going to spend way more time on this tomorrow. Carbohydrates are simple sugars, right? Monosaccharides. Glucose is the most common one. Obviously, we'll talk about fructose as well. That's another one, and galactose. All those are single sugar molecules, right? Glucose is the one that we talk about because, like, you know, that's the one that our body uses for metabolism. You know, if you get fructose in, your body converts it into glucose, but then, poof, you know, it goes through the, you know, glycolysis like it normally would. So when we say carbohydrates, it is a material that's made up of simple sugars. What are simple sugars? Well, those are your mono and disaccharides, right? So monosaccharides, mono for one, is a single sugar molecule. Glucose, fructose, and galactose, right? All of those are monosaccharides. Then you've got disaccharides. Disaccharides are two monosaccharides linked together. So if you have glucose plus glucose, you have lactose. If you have glucose plus galactose, you have maltose. And if you have glucose plus fructose, you have sucrose. And sucrose is the bad one. Sucrose is that thing that is found in every grocery. You know, when you go buy like a bowl of cereal, right, and it's packed full of sugar, it is mostly sucrose. So it is a lot of sugar packed into a very small area, which is why it tastes so sweet. So those are your disaccharides. Then we've got our polysaccharides. Polysaccharides are lots and lots and lots of sugar. You will see there's oligosaccharides. These are semi-simple sugars. If it's like 3 to 10 linked sugars, that's an oligosaccharide. But honestly, if it's more than 3, we just call it a polysaccharide. But like starches, right, which is a lot of carbohydrates all coming together, that is our complex carb. And then glycogen, which is the storage form of carbohydrate, you know, when your body assembles a bunch of carbohydrates together and just kind of stores it off to the side so that it can use it for energy metabolism later, that is also a starch. It is, or at least is considered a starch. Even though it doesn't look like a solid, glycogen is sort of a liquid. It actually, I always say this, but it's kind of similar to like if you've ever boiled a pot of potatoes and there's that scum on the top, that's kind of what glycogen looks like. And so that's stored in all of your muscles and stored in your liver. And that way, like, we can have glucose on the go if we haven't eaten in a couple hours. And then we got fiber. Fiber is like cellulose, right? If you look at like cellulose, like chemically, it's just a really freaking hard material to break down. It is a complex carb just like anything else. But, you know, when you look at those freaking fibers, they're just solid. I mean, there's just no getting in there and breaking that down. You know, it's just too darn complicated. It's all super glued together because of how tightly packed it is. So our digestive system doesn't really do a very good job of breaking down cellulose, which honestly is actually a pretty good thing. Because now it can move its way through our digestive tract and it can actually grab materials and pull them out with it. This is why fiber cleans you out, right? It's also the reason why like cats and dogs, like, you know, like they'll chew like grass on the lawn and stuff. They do that because it grabs fur and like hairballs from where they're licking themselves, and then it just kind of pulls that out of the body, which is a really good thing, you know? If you've ever wondered why your cat's eating on the lawn, you know, eating grass on the lawn, that's why. It's cutting up fur balls. That's also why they put oatmeal in like dog and cat food, even though cats are strictly carnivores. You know, dogs are omnivores. They can eat, you know, plants as well, but like cats are 100% carnivore only. Yet we can still give them a little bit of oatmeal because it can basically not be digested, not absorbed, and then pulled through their digestive tract. And then you know, that's what's going to be in a cat's hairball formula. Fun, weird fact of the day. So carbohydrates are great because they are such a good source of energy metabolism. Your body can break them down for energy very, very easily. And so they're going to be broken down as well. If we have like a big complex carb, we need to have materials that are going to break these down. The first one that a carbohydrate is going to run into is in your mouth. That's your salivary amylase, right? Which is a digestive enzyme in our saliva that converts complex carbohydrates into simple sugars, right? So basically it splits polysaccharides into disaccharides. So salivary amylase is really good at breaking down carbohydrates, but it's not good enough at breaking it down into single glucose. It's not ready for absorption just yet. So, but it does break it down into disaccharides. So, you know, that's why if you've ever like eaten a cracker and you've been eating like a lot of them over like it'll start to taste a little sweet after a while. And that's because like those complex carbs are getting broken down into something that's much simpler and it starts to taste a little sweeter. You've also got pancreatic amylase, a little bit different. This is created by your pancreas, and this is what's helping break down any starches that didn't get broken down, right? So if we are really breaking them down, you know, pancreatic amylase is pretty good at that. And then lastly, you've got what are called brush border disaccharides, which are digestive enzymes that line the walls of your cells. And if a piece of glucose brushes along the border of like a wall in a cell, it will break it down into a simple sugar. And so these are produced by the cells of your intestinal wall, and they take any disaccharides that haven't been broken down into monosaccharides just yet, and finally breaks them down. And so now you are left with nothing but one simple sugar. Those brush border disaccharides, like I said, they rely on like a lot of different enzymes. One of those enzymes could be lactate, and that is what breaks down lactose. So when we have like certain people who can break down lactose, it's because they have a mutation where they create this enzyme. People who can't break down lactose, which is most of the world, 68% of the world, we looked it up last night, you know, that means that you're just missing that mutation. You don't have that enzyme. So carbohydrates and all other nutrients, by the way, I don't know why they're talking about this in the carb section, but I guess, you know, carbohydrates and all other nutrients, they're going to pass into your bloodstream. Okay, so they're going to pass through your small intestine into your bloodstream. The first stop that they're going to go to is your liver, and then eventually it'll go over to the rest of the body. But in terms of like absorbing these things, how does this actually happen? Well, there's a couple different ways that we absorb nutrients, right? And we kind of got to look at like what happens in biology in general. The first one is just very simple passive diffusion. So just showing you what passive diffusion kind of looks like. Remember passive diffusion, remember I've told you if you ever want to understand a little bit about how the universe works, one of the things to remember is that like stuff will always move from an area of high concentration to an area of low concentration. So if you have a lot of carbohydrates over here and very little over here, those carbohydrates will naturally just want to passively move in that direction. Okay. This might have what I want. I don't know this video, but let's take a look here real quick. All right, well, okay, so he has two very different solutions here, right? I assume, yeah, he put glucose in here. Okay, so there's a lot of, or I'm sorry, he's putting glucose in here. So there's a lot of sugars in one, and then this is just regular old water over here. So now he's got like sugar water, and he's got a bunch of like regular water, right? So now what he's gonna do is he's gonna dump that bag in there, and you will notice that materials, the water will actually start to flood into that bag, which is kind of interesting, right? So water passively moved into here because there was very little water in terms of like its ratio. The ratio of water that was in this bag was lower than the ratio of water in the jar. So what happened, because that's a semi-permeable membrane, you know, stuff can somewhat pass through it. Water naturally went, wow, there's a low concentration of water over there and there's a high concentration over here. So that water naturally moved and rushed into the bag. Okay. That is passive diffusion. It doesn't require any energy. It just happens. It's like a ball rolling downhill. You know, it moves from, you know, where there's less gravity to more, you know, like, now there is also facilitated diffusion. Facilitated diffusion is where a protein will actually carry a substance across a membrane. So fat soluble vitamins are a good example of this. They want to move into the bloodstream because there's a low concentration of fat soluble vitamins there, but they can't do it because they just can't get through the membrane. Luckily, if there's some fat, they get carried along with that, and that's facilitated diffusion. It can use protein carrier molecules or other molecules to move substance from one side to another. I always like to think of it as like a shuttle van, you know? Well, sorry, not like a shuttle van. I always like to think of that one as like a line at Disneyland. You know, like you stand in a line and it moves specifically where it's supposed to go, you know, and you have to stay in that line in order to, like, you know, keep moving in the direction you want to go to, which is towards whatever ride you're going on. Active transport is more like a shuttle. So active transport is where there's actually specific substances that will carry stuff from one side to another. This is not as common directly in our digestive tract, but it's definitely happening as well. You know, sometimes materials will actually come up, grab it, and then move it from one side. Active transport's definitely something that our body uses very regularly when it's transporting certain materials across like certain membranes. This is one of the reasons why you have all of your little microvilli, which are all the little hairs that live on your villi that move stuff around. And then you have endocytosis, and endocytosis is my favorite. Endocytosis, it means devouring cell action, by the way. And it is where a substance would be enclosed by a membrane. So this is how your cells eat stuff, right? So a material might be like right here, and then your cell will come up and it will close itself around that, and then it will open itself on the inside. And boom, now your cell has eaten something. This is how your cells, like, you know, eat glucose, right? Like this is how glucose sometimes gets into our cells when we need it to be able to like produce metabolism. So those are the ways that we're absorbing nutrients, both at our small intestine, but also like on a cellular level throughout the rest of our body. That's also happening there. Like I said, once carbohydrates get into your blood, they enter your bloodstream. The first stop they are going to make, they're going to go through your liver first. Okay, that's the first area where like blood travels. Like all of your blood vessels run through the liver because your liver is like, you know, border patrol that's like detoxing anything, you know, making sure it's like, hey, do you have any fruits or vegetables? You know, like we don't want any invasive bugs in the state of California, you know? And so like they're going to stop, you know, any materials that happen to be moving in to make sure that like, you know, there's no foreign substances or harmful things. And if there are, then your liver is basically just going to use a bunch of enzymes to try and destroy everything in sight. This is actually what happens like with alcohol. Your liver breaks down like alcohol. This is why alcohol is so bad for us and causes like cirrhosis of the liver. What's great about that though, what's great about like carbohydrates going through your liver first is if your liver needs, you know, some carbohydrates, it can actually take them and store them right away. This is why our liver stores a lot of our glycogen, right? Glycogen, again, the storage form of glucose inside of our body. It is considered a starch. It is a, you know, a polysaccharide. And so it'll go through there and kind of get stored, right? The rest of that glucose will move throughout the rest of your body. And then your pancreas will create this material called insulin. And insulin's job is to say, hey, sugar, we're glad you got delivered all the way to the left big toe, but we need you to get out of the bloodstream so that the bloodstream can continue transporting other materials and stuff. And so insulin will drive that sugar out of your blood into your cells. That will either result in you getting a whole bunch of energy because all of a sudden glycolysis and you're producing. This is why eating sometimes gives us energy, or it will get it converted and turned into glycogen to be stored and used for energy later. Or if your glycogen stores are already filled, it will convert it into fat, and then it will store it as a triglyceride for long-term storage. And this is why getting rid of fat is sometimes so difficult, because we don't tap into long-term storage. That's our emergency fund. We tap into our regular bank account. That's your glycogen. So you have to burn through your bank account first before you tap into your savings. And there are glucose transporters, your GLUT1 and your GLUT4. These are basically just carrying glucose to, maybe muscle cells or, wherever it needs to go within the body. But don't worry about those. We're not going to see those ever. So that's carbohydrates. Any questions on that so far? Cool. All right, let's look at fats. So lipids, or fats, are made up of individual fatty acids. There's a couple different versions out there. We've been talking about these. When we talk about like what a lipid is, right? It's an organic compound, right? And there's a couple different versions. There are triglycerides, which is the one that we mostly talk about, right? This is a glycerol attached to 3 fatty acids, thus triglyceride. And that is, when you think of like saturated fat or unsaturated fat, when you're consuming foods, you are consuming triglycerides. Or when your body builds up, like I said, like excess glucose, if it can't be stored as glycogen, it'll get converted into triglycerides and then stored within a fat cell, So a triglyceride is definitely a really high source of energy, but there's also diglycerides. These are more commonly referred to as phospholipids, and that's 2 fatty acids attached to it. When you look at your cell walls, I just looked up endocytosis, right? And we saw it kind of looked like this, right? This picture here. Well, take a look. See that double layer right there, the yellow on the outside and then the kind of brownish yellow on the inside, right? That's a single little bit of glycerol, and then there's 2 little fatty acid tails. And so that's one layer, and then there's another layer. This is what's called your phospholipid bilayer. It's 2 layers of phospholipids. And that's how our body is going to separate water from one side of a membrane to another, So those are diglycerides. And then you've got monoglycerides, which is 1 little fatty acid. This is something you would typically want to avoid in your diet because they're not used for metabolism very well. They're often just immediately converted and stored as triglycerides. You can find monoglycerides in food generally. In fact, if I look up monoglyceride, I'll probably get a big picture of margarine. Yeah, you'll find it in baked goods, butter alternatives, trans fats, peanut butter, things like that. Yeah, there we go. They'll often put a lot of monoglycerides in like a lot of like heavily processed foods. They're really great at extending the shelf life of something because bacteria does not eat monoglycerides very well. So it's pretty good to use as like a preservative, but it's not exactly good for our body. And then we're breaking everything down in order to just get our individual free fatty acids. A free fatty acid is a fatty acid that's been cut from a triglyceride. It doesn't have its glycerol molecule anymore. It's just the fatty acid. This is used directly for aerobic metabolism. So our body loves breaking down triglycerides because it's going to be able to get 3 individual fatty acids, which means it's going to get plenty of energy, right? It can go straight through your energy metabolism. So triglycerides, a few of them are going to be broken down in your salivary glands. You do have this stuff called lingual lipase, which is similar to salivary amylase, except that it's lipase, so it breaks down lipids, right? But then some of it will also happen in your stomach, a little bit of gastric lipase as well. But for the most part, the heavy lifting of fat digestion takes place in the small intestine, thanks to your gallbladder and pancreas, where you're really using those bile salts to kind of break everything down. So lingual lipase is, released by your tongue. This is why you can taste fats. Gastric lipase is secreted by your stomach. Pancreatic lipase is created by your pancreas. And then your liver is creating that bile that we talked about earlier. Now, we talked about how like some things need to be transported with the help of like certain proteins and certain enzymes, right? We talked about fat-soluble vitamins need to be carried by fat. Well, this is where we have to talk about lipoproteins, which is not its own type of fat, but it's a fat molecule attached to a lipid molecule. This is your cholesterol, okay? Lipoproteins are your cholesterols. And so these are substances that are transported by the lipids in your blood, right? You have two major classifications. LDL cholesterol, which is your low density lipoproteins. They are basically high in cholesterols and low in, fat. This is often what we think of as like your bad cholesterol versus your high density lipoproteins, which are, dense in fat and low in cholesterol. This is your good cholesterol. So we're trying to find a balance between how much LDL versus HDL we are consuming in our diets to make sure that we don't have too much of that low density stuff. That low density stuff, generally tends to like carry triglycerides for more fat storage. Your high density stuff carries fats in order to be converted into hormones, which is why, cholesterol is actually a very important part of like having proper hormonal function. And here's this whole process as you can see it here, right here, right? We have like a long chain fatty acids, like a fat droplet with like some cholesterol in it, fatty acids, phospholipids, monoglycerides. And then basically all of that's going to get broken down into their individual components. You've got a little phospholipid over here, a little monoglyceride over here, and a little bit of triglyceride over here. And then boop, it gets into your blood system, lymphatic system here, and then blood flow here. And it's absorbed by the body just like everything else is. So that's fats in a nutshell. Any questions on fats, guys? Nope. All right, then we got proteins, right? Proteins, big complex chains of amino acids, right? So an amino acid is carbon, hydrogen, and then it's got this special nitrogen skeleton. And because that skeleton can shape itself in 20 different varieties, we have 20 different amino acids. So when we are breaking down proteins, right, we call it denature them or break their peptide bonds. And basically that straightens out their shape and makes it easier for us to like break down. You've actually seen denatured protein. You have seen denatured protein if you're anything like me, and you have, and you've been cooking. Oh, really? Not seeing an example? That's so funny. Let's see here. Burnt food. If you've ever been cooking and you have burnt your food and you've converted it into freaking carbon, right? Those are denatured proteins. You unfolded their natural shape, and now they are shaped very differently, and do not have the same nutritional value. You basically destroyed some of those amino acids, right? So that's kind of what a denatured protein looks like. Obviously, that can happen inside the body as well. That's how our body is breaking stuff down in particular, right? So what will happen is once your proteins are broken down, right, or denatured, and that can happen because of like excessive heat, or it could happen from chemical differences, right? This big, interesting shape over here, it's kind of getting straightened out into a much simpler shape. And now all those individual amino acids can be cleaved off of there. And you can see what that kind of looks like right here, right? Imagine that's an amino acid, that's another one, that's another one, right? We can break each individual amino acid off, and now it can be absorbed by our bloodstream. So again, we're breaking down proteins into amino acids so that those amino acids can be absorbed into the blood. So one thing that we do talk about is that we have what's called an amino acid pool, which is a collection of amino acids. These are either found in like certain body tissues in case protein metabolism needs to happen near those tissues, or it's just flowing around in like bodily fluids. So your amino acid pool, this is where like, you know, we talked about like veganism and making sure that like you're getting a complete amino acid profile. You have to pair two incomplete sources together so they complement each other and fill in each other's gaps, right? Well, what happens if you didn't do that? You know, if you ate like a brown rice at one meal and then you ate beans at the next, well, thanks to your amino acid pool, it's like, okay, well, you were able to catch up later and fill in those gaps. So it doesn't always necessarily have to be at the same meal. But it can be, you know, if in fact, if it is, then you're ensuring that it's happening. And this is kind of what protein synthesis looks like. You know, this is actually more of like building stuff up. This is actually an anabolic process, but basically your DNA has a little blueprint in it. And then it creates what's called RNA, which is basically like a copy. And then that RNA is basically saying like, hey, this is how we're going to assemble those proteins, put them in this order. And when that happens, that changes their shape into whatever protein you need it to be made. And then you get these little cells called, these little organelles called ribosomes, which are actually assembling it. But anyway, don't worry about that. What we need is like proteins, right? We're basically being like, all right, we got 20 ingredients, we break them apart, and then we assemble them in whatever order we want them to be in order to make like new tissues in the body. And then we've got minerals, vitamins, and water, right? So these are our more trace, you know, things that we need in smaller amounts, I mean, with the exception of water. Water you need lots of, but we're actually not talking about water today. Vitamins are, you know, materials that you need like milligrams of each day, right? These are materials responsible for, you know, they aid in certain physiologic and metabolic processes, right? So like water soluble vitamins, they are, you know, vitamins that dissolve in a watery, I should say mix, not mid, mix of food and are absorbed along with water. So they need to be carried by water and they need to be, you know, that's that facilitated diffusion, right? It's like somebody going up to a bouncer and be like, he's with me, right? And then they come in with you. B vitamins and all of your B vitamins and vitamin C, those are all water soluble vitamins. If you get too many water soluble vitamins, you know, we're going to talk about vitamin toxicity in the next couple of days. But if you get too many water soluble vitamins, it's going to cause problems. It can, but it's pretty rare. Most of the time when you get too many water soluble vitamins, your body just pees it out. This is why if you've ever taken like a multivitamin and then you've gone to the bathroom and it's like bright yellow, like it looks like freaking highlighter fluid, that is the extra B vitamins being peed out by your body that your body doesn't need. It's riboflavin. Then you get your fat soluble vitamins. These are actually going to dissolve in fats and they are carried by fats. So vitamins A, D, E, and K, a lot of these are acting as like antioxidants. They have really positive effects on the body. And then they do interact with our metabolism as well. So, you know, all very, very important stuff there. Actually, it doesn't have, yeah. And then minerals, which are not really being mentioned here, are inorganic substances that basically make up certain body tissues, and they do aid in certain physiologic processes, right? So like calcium makes up your body, but it also is what attracts, you know, troponin and tropomyosin, which is going to ensure that like those materials move out of the way, and that allows for muscle contractions to occur. So we need calcium, you know. Well, we also have sodium and potassium, which have a slight different electric charge. So if you were to move sodium and potassium back and forth like this, what does that do? It creates not static electricity, but it creates electricity, right? And so those are our electrolytes, sodium and potassium. They aid in our body's ability to generate electrochemical signals, which is how we do everything. That's how our body communicates, you know? That's why our nervous system is considered the communication network. All right, questions so far? Lorianne and Bay, how you feeling? I know a lot of this has been review, but hopefully getting a couple new nuggets. Feeling good? Cool. All right, well, let's look at energy, right? How do we measure energy? What are we talking about when we say energy? Well, if we're talking about your energy metabolism, right, we are describing how your body is generating energy, how it's generating ATP, right? Because we can't really, we can't convert it into energy directly. If we did, it would just heat us up every time, right? And then we would overheat. So instead, we create ATP molecules where we can do a controlled burst of energy release. So your energy metabolism is how you are generating ATP, and that is what we refer to as like our metabolism, right? Your metabolism is the total energy required to power everything that your body does, every chemical reaction you've got. Now there are two terms that kind of describe how fast your metabolism is running, and that is your basal metabolic rate and your resting metabolic rate. These are essentially the same thing, but they are slightly different. Your basal metabolic rate is the minimum amount of energy required to sustain life in an active state. So if you were awake, but you just laid on the ground and didn't move, but you stayed awake for 24 hours, right? The amount of energy that you burn because you were awake, that's your basal metabolic rate, right? And that's usually what we're actually measuring for the most part. Your resting metabolic rate is the minimum amount of energy required by your body at rest. So if you were literally like conked into a coma and like, barely just like kept alive, don't even necessarily have to breathe or anything like that, that's going to be your resting metabolic rate. Like I said, they're essentially the same thing because we never actually measure either of those situations that way. We kind of just use like a mathematic formula, but it's going to describe how many calories worth of energy you burn every single day and how much ATP you are generating. So just really quickly reviewing what ATP is, don't worry, it's not here in your notes, right? It's a molecule of adenosine with 3 fatty acids attached to it, right? And so, not fatty acids, God, sorry, that's a triglyceride. 3 phosphates attached to it. So adenosine triphosphates. And so we store a lot of energy in that 3rd phosphate, between the 2nd and the 3rd one. So when we break off that 3rd phosphate, that energy is released, boom, we get a big burst, right? Then you're left with ADP, or adenosine diphosphate, and that's 2 phosphates, right? There's still a little bit of energy trapped between those phosphates, just not quite as much. Our body will not really burn up ADP unless it has to, but if it does, it'll convert it into AMP, which is adenosine monophosphate, and there's very little energy there. Creating AMP has been shown to inhibit muscle building, actually. Because it's much more used for like long duration, super intense. This is one of the theories behind why like marathoners, they do work out regularly. And obviously like the answer to why they're so skinny is because they burn so many calories. But sometimes they have a hard time building muscle. And this is one of the reasons that kind of explains that actually. It creates a lot of AMP. Oh, that's right. This is kind of a weird bit right here. I remember this now. There is a little bit of review here, just looking at a cell. Remember, your cell membrane, that's the outer like shell of your cell. It's made up of that phospholipid bilayer. And then inside your cell is all kinds of fluids. And then outside your cells, all kinds of fluids as well. There's water in and water out. That phospholipid bilayer is what separates the water from getting in to getting out if we don't want it to. But it's also what allows like certain materials to move in, because you have these organelles, little pieces inside of your cells that do specific functions. The most important one that we are going to talk about is your mitochondria, right? But technically the fluid itself is its own like organelle to talk about. The cytoplasm is also very important because within the fluid and within the mitochondria, those are the 2 places where we are generating energy. So if we're looking at this is the metabolic factory, right? This is an analogy. When it comes to energy metabolism, you get your blood, which has some macronutrients in it, right? Those macronutrients come in and, those are your proteins, fats, and carbs. And, a little bit of oxygen comes in as well. And what happens is your aerobic and anaerobic energy systems and your phosphagen systems basically convert all of that into ATP and then spit it out. Now, if it did it through the anaerobic system, it's also going to make some lactic acid. If it did it through the aerobic system, it's also going to make some water and some CO2. And that's why lactic acid, CO2, and water are little byproducts over here. So there's nothing in your body that actually looks like this picture here. This is just an analogy. But if you were thinking of it as like a factory, right? Here's the chimney where all the byproducts and like smoke and stuff is coming out of the factory. And then here's the stuff going into the factory. And then here's the stuff coming out of it. So I love this picture. Even though nothing in your body actually looks like this, I love this analogy. I think this is a really helpful way to kind of look at it, right? I always like to say ingredients go in, products and byproducts come out, right? And I love this one here too, the phosphagen energy system. Notice how there's nothing going into it. It's just kind of bouncing back and forth. That's because you just have passive creatine that's allowing that one to happen. But let's go through them. So your phosphagen system, more commonly referred to as the ATP-PC system, the adenosine triphosphate phosphocreatine system, or the ATP-PC system, or I'm sorry, CP system, adenosine triphosphate creatine phosphate system. That's how I learned it, by the way, but then apparently they relabeled it after I left. But the ATP-PC system, just call it the phosphagen system. It's way easier to say. And basically your body is just reconstituting ATP by breaking down a phosphate that's found in a creatine molecule. Then the real work of creating energy comes in, and that's your anaerobic and aerobic metabolisms. Anaerobic is all the stuff that takes place in the absence of oxygen. So this happens in the cytoplasm, in the fluid portion of your cell, right? So your anabolic pathways require energy, and they result in the formation of ATP, but you also get some lactic acid, right? So it takes, anabolic metabolism takes very simple things and builds them up into more complex substances. It takes in something very simple like glucose and spits out a bunch of ATP, right? That's your anabolic pathways. Actually, I'll come back to these concepts in a second. Let's actually leave this alone for now. Let's not worry about anabolic and so looking at anaerobic, right? Anaerobic, meaning without oxygen, generates ATP in the absence of oxygen. Aerobic, we need some oxygen. So we go back to our little factory here, right? Notice how carbohydrates are the only one that can go into the anaerobic system, right? Fats, proteins, those have to go into the aerobic system. But carbohydrates have to go through the anaerobic system. And they spit out ATP, but their byproduct is lactic acid, right? That's an anaerobic pathway, no oxygen here. That's why it ferments into lactic acid, because there's fluid in the cell, no actual air. Your aerobic pathways, right, are taking that lactic acid and actually using it, but we're not seeing that in the picture here. But basically proteins, fats, and carbs can all go through the aerobic system and spit out some ATP. So anaerobic is able to generate ATP in the absence of oxygen. Aerobic requires the presence of oxygen to generate ATP. Okay, and here's sort of how those rates work, right? Your phosphagen system is very much not very complex, and it produces ATP really quickly. Anaerobic is moderately complex, but it runs pretty freaking close. It's kind of similar to the phosphagen system. And then your aerobic system is very complex, and it's very slow, but it produces energy, it creates a lot of energy very slowly. Right? Because your aerobic system requires this system to happen underneath it. So if that's not happening, it kind of has to wait, right? It has to wait for a delivery before it can manufacture anything. So in terms of complexity, phosphagen is really simple. Glycolysis is kind of complicated, but the aerobic metabolism is very complicated, right? Krebs cycle and electron transport chain. Your phosphagen system produces ATP really quickly, but it doesn't produce very much of it at a time. Your glycolysis produces ATP really quickly as well. Not as much as the ATP, not as fast as the ATP-PC system, but it's able to generate more, which is nice. but it still has a limited capacity. And then your aerobic energy system creates large amounts of ATP very slowly. So you're getting like 2 ATP in glycolysis at a rate like this versus like 36 ATP, and then we wait. 30, it's a little bit different, right? And that's why that's why it's our endurance, right? It's low intensity, long duration exercise. So when it comes to like your capacity for how much ATP you can generate, again, go back to our little factory picture here. Notice how that anaerobic system, glycolysis, can only do it if there are carbs. What happens if you run out of carbs? You have to entirely rely on your aerobic energy system, which is going to be freaking tough, right? So when we look at like the capacity to make ATP, right? The phosphagen system's capacity for that is essentially unlimited because creatine can just kind of resynthesize itself and just, you're resynthesizing ATP. You're not making new ATP. Glycolysis, though, is kind of limited, right? This is like very, very limited. You can run out of how much ATP you can make because you run out of carbohydrates. Your aerobic metabolism, which is where you are generating it from fats or maybe even proteins, it's essentially unlimited. The amount of calories that you have stored on your body in terms of fat is a very large number. It's not actually unlimited. I'm sure we could, calculate how many pounds of fat are on you and calculate how many calories are within that and then break that all down and figure out, be like, oh, okay, you've got, 384,296,812 calories worth of fat on your body. That's essentially unlimited, at least in terms of like the practical way that we would use those numbers. We only burn, like we said yesterday, about 2,000 calories a day on average, right? Some people more, some people less, but like the amount of energy you have stored in terms of fat on your body, we can just consider it an unlimited amount. So looking at supplying ATP during like sports performances, right? You've got your aerobic and your anaerobic energy system. Aerobic is the low intensity stuff, right? This is going to require your other energy systems to happen first. And this is that chart that I drew for you guys the other day when we were at Sochi, right? Notice how their version's a little bit different, right? You can see, right, this line right here, that's your phosphagen system. So when your intensity is really intense and your duration's really low, phosphagen system supplies a lot of your energy and then it kind of dies off. Meanwhile, glycolysis starts to kick in. And, in moderate duration, right here in the middle, this is supplying most of your energy. And then it also kind of dies off. Meanwhile, your aerobic system starts moving and it basically never has to stop. Because again, you have an unlimited fat supply. As long as you can bring in oxygen and as long as you got fat on your body, your aerobic energy system can keep powering your body and keep you running. Essentially unlimited, at least in terms of how we use it every day. Questions on any of that, guys? Before we move into the last little bit here. Cool. All right, so let's go ahead and look at our metabolic pathways, breaking stuff down, building stuff up, right? So you've got either the breaking down of stuff or you got the building up. Anabolic pathways that are building up, right? This requires energy and it forms complex molecules. So it takes something very simple and builds it into something that is much more complex. When your body assembles a protein, that's an anabolic process, right? Catabolic processes actually reduce energy, right? They reduce compounds into something a little bit simpler, right? So they break down materials into their base parts. So if you look here, glycogen gets broken down into glucose and energy. That is a catabolic reaction. Triglycerides get broken down into glycerol and fatty acids. That is a catabolic reaction. Protein gets broken down into amino acids. That is also a catabolic reaction. But there's also some byproduct associated with this one, which is going to be your urea, which is what makes your pee smell. Anabolic reactions are the opposite, right? If you took glucose and you added some more glucose and your body created some glycogen, boom, that took a little bit of energy in order for that to happen. And so that's an anabolic reaction. If you were to, take a little bit of glycerol and some fatty acids and make a new fat cell, create a triglyceride, boom, that also takes a little bit of energy, right? Or if your body assembles some amino acids to make like a new protein, that also requires energy. So catabolic reactions release energy, anabolic reactions use energy to build stuff up. And by the way, this is what, just as a chart form, this is what glycolysis looks like. Glucose basically gets broken down into all these individual materials happening on kind of both sides of the chart here. They become a little bit of NAD and FAD, and they become a little bit of lactic acid. Well, they become pyruvates. Then those pyruvates ferment into lactic acid. Then you've got the Krebs cycle here. You can see where like that NAD and FAD basically come in and they kick off this whole energy. They create more NAD and FAD. And then that gets, all these individual little enzymes that kind of break off a little bit of that NAD and FAD every time. And it does spit out some energy, right? You end up with about 2 molecules of ATP in the Krebs cycle as well. But then here's the electron transport chain. And this is where all that NAD and all that FAD with all of its electrons get squeezed together through this little protein right here and spits out 36 molecules of ATP. So we get a lot. So the citric acid cycle or the Krebs cycle and the electron transport chain, both of these are aerobic processes, whereas glycolysis is an anaerobic. This takes place in the fluid. These both take place in the mitochondria. And here's the process of glycogenesis. There's just a lot of charts here at the end of the slides. Here's glycogenesis. This is how your body makes glycogen. So glucose, and it just starts linking all those glucoses together. That's great because eventually it can go through, the Krebs cycle, or it could go through, anaerobic glycolysis, whatever. Oh, it's funny. I thought lipolysis was going to be next. There's also lipolysis where your body makes fat, Lauren, any question?
Yeah. What is the NAD and FAD again? I need that little portion repeated, please.
What are NAD and FAD?
Yeah.
NAD and FAD are actually byproducts of the Krebs cycle. They're actually technically called NADH and FADH2. Basically, if you were to look at them, let's see here. Yeah. So here's what here's what NAD and FAD actually look like on a chemical level. You can see there's a little bit of like nitrogen, like they're almost like little proteins, right? And when you look at them, they have, you can't really see it here. They're not really given, hold on. Yeah, this works. This is fine. They kind of got it circled right here. You can actually see. See how there's a little bit of hydrogen? So hydrogen is number 1 on the periodic table. It's full of like protons. And so whenever we talk about like, if there's just like, if you're talking about like a proton accelerator, it's like talking about, oftentimes they're using hydrogen. They're just stripping the protons away because hydrogen has 1 proton, which is a positively charged element, right? Electrons are the negatively charged elements. There's normally an equal amount, but not always, right? So these have a lot of, like what NAD and FAD are, is they're these high energy, like little electrons and protons. And when you squeeze them all together, all that energy gets transformed and attached to, your phosphates and your adenosine molecules, right? So it all gets squeezed into and eventually becomes ATP. If you want to think of it as like, remember how I said it's really hard for us to store raw energy? Think of NAD and FAD as like raw energy. And so if we didn't convert them directly into like an ATP molecule, we wouldn't be able to hold on to it. It would just be released. So what the electron transport chain's job is it uses this little protein right here. And you can see a little bit of hydrogen, right? Those are the little protons. They go through this little pump right here, and it squeezes them all together to convert it into a little bit of ATP and a little bit of water. There's a little bit of water left over afterwards. And so then the cell spits the water out. And that's why water is also a byproduct of the electron transport chain, and CO2. Yeah, the remaining carbon that was left from that carbohydrate also gets spit out. Actually, you know what? Here we go. This is great. Yep. See all this? See all that hydrogen, all those little protons right there? They're going to get squeezed through this little pump until eventually they become like a bunch of ATP. So that's what NAD and FAD are. They're byproducts of the Krebs cycle that have a lot of protons that haven't become energy just yet. Does that answer your question?
Yes, thank you so much.
Yeah, no, you're good. That's a tough one. I honestly, like, that's my best understanding of it. Some of like understanding NAD and FAD is pretty freaking deep when you really get into it. But that is how it works. Whether or not my explanation was actually like perfectly scientifically sound, the way it works is sound. If we're looking at summarizing everything up, right? Digestion is the process of breaking carbohydrates into monosaccharides, breaking fats into fatty acids, and breaking proteins into amino acids. Your body is then going to absorb all those materials into your bloodstream so that it can anabolically build them up into something new, or use those ingredients to catabolically strip their energy and break them down into something also new. Like anabolically kind of takes energy, catabolically sort of like releases energy. So digestion is releasing energy. You will often hear the phrase catabolism fuels anabolism. Catabolic reactions, like digesting food, allows us to anabolically do everything it is that we do every single day. A lot of this is thanks to, and by the way, not all of this is like passive, some of it's like acid in your stomach and stuff, but a lot of it is like chemical reactions. We need enzymes in order for this to occur. Enzymes are complex, they're proteins. That's what an enzyme is. It's a protein. And so like your body will sometimes be digesting stuff so that it can make stuff to further digest stuff later, which is kind of fun. And so that's happening there. Meanwhile, fats, those are being absorbed directly into your small intestine as well, and they can be used directly for energy if your intensity is low enough, or they can be used to make up like new cell membranes, can convert it into hormones, lots of other materials. Vitamins, minerals, and water are also definitely an important nutrient that we talked about today. Minerals are acting as, some of them are acting as electrolytes, allowing us to have electrochemical signals. Vitamins are interacting with the body that are allowing metabolic functions to occur. Very big stuff there. And then we kind of wrapped everything up today by talking about our energy systems again, right? We start with glycolysis. That creates a little bit of ATP, but it also creates that pyruvate. And because this is in the fluid of the cell, which is anaerobic, it ferments into lactic acid. Yep. And then lactic acid goes through the Krebs cycle, passes into the mitochondria. That spits out some more ATP, but really what it creates is a lot of NAD and FAD. NAD and FAD then go through the electron transport chain. That's where we get lots of ATP. Pretty crazy, right? We're the world's greatest recycling system. We create a lot of stuff and then we use it later,
Yeah, it's pretty awesome. Talk about believing in a higher power.
Yeah, right? Amazing that any of this was able to occur.
Yeah, unbelievable. All right, cool.
All right, and that's it.
Thank you so much.
We got a big PowerPoint tomorrow. It's going to seem like I'm moving really fast, but it's meant to replace your textbook. There's no textbook for nutrition, which is a bummer. There's a lot of
4 and 5, right? Thursday and Friday.
So it'll be a long one. It'll be a long one tomorrow. But
okay, cool.
All right.